Today we're going to be talking about kinematics in physics. Kinematics is defined as the description of how an object moves. Right here I have a picture of two worlds, you can say. A perfect world, which would be in a vacuum, and then our reality world that we live in. In a perfect world, in the vacuum, there's no such thing as air resistance to hold back an object to give it its full amount of energy. However, since we don't live in a perfect world in a vacuum, we have this thing called air resistance, which prevents that ability. So we're going to be talking about two types of energy today. We got kinetic energy, which is abbreviated as Ke, and potential energy, which is abbreviated as Pe. Both those together combine to equal mechanical energy, as abbreviated as Me. So when we're looking at mechanical energy, we want to find usually the change in energy. So delta T, which represents the change in energy, equals mechanical energy of final minus the mechanical energy of initial. If you break this down into both components of kinetic energy and potential energy, you have what is known as delta E equals kinetic energy final plus potential energy final minus kinetic energy of initial plus potential energy of initial. This enables us to learn an exact point of an object's energy level. So we're going to be using that today to find a moment of energy in a ball that's falling from 10 meters in the air. So, if we have a ball at 10 meters, right here, and it fell to right here, it would bounce back up. That would come back up in a perfect world. However, energy is transferred from into this potential energy all the way at the top when there's no kinetic energy, when it's not moving, all the way down to this potential energy. However, there's some energy in this moment where it's converted to flatten this object, to compress it, and then to release it back into the air. So depending on how dense the object is, it can go up to 2.5 meters high, or it can go up to 7.5 meters high. However, it will never be able to reach its full potential back up to 10 meters because of the law of conservation of energy, because it's not created nor destroyed, it can only be transferred. And the ball energy gets transferred into the ground as heat or the compression. So, if we have the ball at 10 meters, that's the height of the ball being dropped. We can look at and find the exact point of energy it has right here and then here. So at the top it's kinetic energy plus potential energy. And then at the bottom it's kinetic energy plus potential energy. If you look at this, at the very top at 10 meters, the ball is not moving. Therefore, the kinetic energy is 0, because if you look at the energy equations, kinetic energy equals 1/2 mv squared. And potential energy equals mgh. Down at the bottom, if you look at potential energy, there's no height. So potential energy would have to equal 0 as well. To find the change in energy here, we equal then the potential energy at the top minus the kinetic energy at the bottom. You can write in the full amount, and then the kinetic energy initial will be 0 and the potential energy final will be 0, but I just made it a little bit shorter and cut that step out. So the laws of conservation of energy says that we can make this equal 0. So if this is equal to 0, then that states we can move this around and make the energies equal to each other. So we have the kinetic energy at the top equal to the final kinetic energy at the bottom. Rewriting these into their forms, we have mgh equal to 1/2 mv squared. And this is where the law of conservation of the vacuum comes in play, because in a perfect world, the masses cancel, and it has no, this is totally irrelevant to the mass. Every object would fall at the exact same rate, no matter what. However, we don't live in a perfect world, and we'd have to calculate the air resistance. But another time, another lecture. So right now we're solving for velocity. We want to know the final velocity of the ball right before it hits, the second before it hits. So we can rearrange this equation, times this by 2 to get to both sides, and then square root the v to get v equals square root of 2gh. So if you want to plug in these, all the numbers, we have the square root of 2 times gravity, which is 9.8, and then the height, which is 10 meters. This equals 196 for v, and then the square root of that, which would be 14 meters per second. That is our final velocity right before the ball hits the ground, which is awesome. Now we have final velocity. What if you want to know how long it took for it to go from the very top to the bottom? We can calculate that as well, because now we have the velocity beginning and final, which the final is 14 and the beginning is 0. So using the equation v equals v naught plus at as acceleration would be gravity, because it is in a vertical dimension, and v naught 0, we have 14 meters per second equals 9.8 meters per second squared times time. If we divide 9.8 meters per second squared, those cancel. You have 9.8 meters per second squared over here. The meters cancel, and one of the seconds cancel. This equals 1.4. And since the seconds is on bottom, under another fraction, it reverses to get 1.4 seconds. And that is how long it takes a ball, or any object in that matter, to reach 0 from 10 meters in the air.